a current-carrying coil of wire. How do you increase the strength of electromagnets? By increasing the current through the magnet. And how often do you use electromagnets? They're a part of everyday life.
So, magnetic fields are made, we've talked about this before, but it's worth mentioning again. Magnetic fields are made by moving charges. Okay? What is an electromagnet? Electromagnet is a coil of wire with current, because current is moving charge, so it creates a magnetic field. So when you have current going through something, it makes a magnetic field. You can use that to attract things. So if you don't have a bar magnet that's always magnetized, you can run current through a wire and make it a magnet for a short period of time, just while the current's going. The nice thing about electromagnets is you can turn them off. You can't turn magnets off. Like bar magnets that we used in that lab, you can't turn them off. But you can turn electromagnets off just by stopping the current. How do you increase the strength of the field? You increase the current. And you use them every day. All right, let me see if there's anything else I want to add there. We'll do that in the clarifying. Okay. All right, let's look at the clarifying stuff. So clarifying.
So to strengthen an electromagnetic, you have to add more current and add more turns in the coil.
Okay.
I'm not sure about the turns in the coil.
Yes, no, you're right.
So then after that, moving charges produce more magnetic field, and current also produces more field.
Yeah. So here's what a electromagnet looks like. So electromagnet has. Oh, do you have it? Oh, you do have a drawing. Oh man.
Isn't it a cool drawing?
It is an excellent drawing.
I just popped
Snap. We'll get to that in a second. I do want to add one more thing here to the clarifying, and that's this. What direction is the field? That's a great question, myself. The direction is around the wire.
Oh, yeah.
So the electromagnetic field produced by an electromagnet is in a circle around the wire. It's not out, it's not up, it's not down, it's not straight. It's in a circular path around. That's very different than what we've done. And it uses something called the right-hand rule, which we'll talk about more tomorrow.
Oh, that's like rotation.
Yeah. So there's two right-hand rules. You're going to get confused, so just mentally prepare yourself for that.
Why isn't the other one called left?
Because the left-hand rule is backwards. So you could do the left-hand rule, but you'd have to make everything backwards. So like whatever you got for your answer, it'd have to be opposite day, and then you get it right. I know. So we're going to do two right-hand rules. One right-hand rule is going to help us figure out the direction of the magnetic field produced by wires, and that's what we're going to do first. That's what this one is. And then the second right-hand rule helps us figure out the direction of force. So what direction is the force acting on these charged particles? Because if moving electrons produce a field and they go into a field, those fields are going to interact with each other and push on each other just like electric charge did. Right? If you put a positive next to a negative, they pushed or pulled on each other and created a force. Same thing is going to be true with magnetism. You're also going to have a force produced that way. So that'll help us figure out that. And yeah, unfortunately, they're both right-hand rules, and unfortunately, they're both completely different. But we'll talk about both of them to help you out there. So let's summarize this sucker.
Okay. So
the summary is pretty much like a combination of the first two. But magnetic fields come from moving charges and when you change current. When a wire is looped, the magnetic field also follows that loop. And when it's coiled, then it follows the coils and it creates an intensity in the middle. And that'll create an electromagnet. And strength of the electromagnet is increased by passing more charge through the water.
Good. So magnetic fields come from the charges and the current. So the big takeaway from this section is what creates magnetic fields, moving charges, and current does that. So whenever you did the labs last unit, you were making magnetic fields. If you had brought a compass into the lab and put the compass on top of the wires, you would see a magnetic field created. Okay? And then the second thing is understanding how electromagnets work. And electromagnets are a combination of how strong the current is and how many loops you do. Because if each loop produces a field going into it, then if you put a whole bunch of loops in a row, you'll create a bunch of fields going in. So the more loops you do, the more field you create. So if you want a massive electromagnet that can say, I don't know, pick up a car, okay, like they have at junkyards, you just need to have these massive, massive currents with massive loops of wire, and it'll create a really large electromagnet. One year for a project, I had a student create an electromagnet that could lift up, what did they bring in? They brought in like 50-pound dumbbells and were able to lift the 50-pound dumbbells using their electromagnet. So you can make some really, really strong ones. Okay? All right, any questions for this group?
Eric got one in the back.
Yep.
So if you put the coil in like a spiral, would that work as adding more loops instead of just like a bunch of different tiny loops?
In a spiral.
So like it's increasingly just going in one.
Oh, I see what you're saying. So if you made, yeah, I see what you're saying there. Yes, to an extent. As you make it further out, the field going through the middle will decrease, but you can make like a thicker one. Usually what people will do is they'll make a long one with several layers. So you could do, yes, like a spiral increasing outward one, but usually what you'll do is you'll increase it forward and outward. But yes, you can do that. Okay? Any other questions for them? Sweet, sweet, sweet.